This is part 2 on our discussion about polarity of molecules. Let's start with CO2. So CO2 here is composed of carbon, then dalawang oxygen bonded to the carbon. They form a double bond with carbon in the center. And from this electron dot structure, we can determine the VSEPR shape. The shape for CO2 is linear. So we have this actual shape for CO2. So it's important to really understand the previous lessons about chemical bonding and the VSEPR theory before diving into this new topic. So it's impossible for you to understand this without your prior knowledge about those topics. So let's go to carbon here. The electronegativity is 2.5. Meanwhile, for oxygen, that's 3.5. So it's composed of two bonds, by the way, this bond and this bond. Let's focus on this bond first. Again, here we have two electrons shared by carbon and oxygen, but they have different electronegativity, 2.5 and 3.5. So these two, now these electrons over here will move closer towards oxygen, right? Because this is much more electronegative compared to carbon. This gives oxygen a partial negative charge and carbon a partial positive charge. Another bond over here, again, it's still oxygen 3.5, so 2.5, 3.5 unequal sharing. So this gives, so here we have this electrons will move closer to oxygen, giving it a partial negative charge, and this becomes partially positive. So CO2 is composed of two polar bond. Again, this one is polar bond and another polar bond over here. But what do you think is the overall polarity of CO2? Because again, it is composed of two bonds over here. So here just add the vector. So this vector, so just add these vectors over here. This is the first vector and this is the second vector. And let's use the head to tail method to add these vectors over here. Let's use this first vector. It's the first vector. Then the second vector will start from the head going to the tail. So here the resultant vector is 0. So as you see here, this vector, this cancels this vector over here. So this cancels the charges here. So overall, actually, this one is a non-polar molecule. A non-polar molecule. Let's consider H2O. H2O is a different molecule. So we have here H2O, hydrogen, then hydrogen. Then we have dalawang lone pairs. Then its VSEPR shape is bent. That's oxygen, hydrogen, then hydrogen over here. Then we have the lone pairs on top. The shape for CO2 is actually bent. So let's write the electronegativity here. For oxygen, that is 3.5. For hydrogen, that is 2.1 and 2.1. So let's focus here first. 3.5 and 2.1. This is much more electronegative. So these electrons will move closer to oxygen. This gives oxygen a partial negative charge. This becomes partially positive. The same thing for this side. This one is much stronger. So these electrons will move closer here. This will become partially negative. This one will become partially positive. So the same thing is composed of two polar bonds. This one is a polar bond. The same thing for this one, also a polar bond. But what do you think is the overall polarity for the molecule? The same thing, we can add the vectors by using the head to tail method of adding vectors. The first vector is this one. So let's write that first, this one. Then we have the second one over here. Again, this one will start from the head going here. So what's the resultant vector? The resultant vector for this is this one. From the tail of the first vector to the head of the second vector. So here, the overall vector for this one is this one. So this one is partially negative and the other one is partially positive. So here, this one is a polar molecule. There's a separation of charge. Again, the top is partially negative and the bottom is partially positive. So as you see here, the shape of the molecule affects the overall polarity of the molecule. So CO2 is linear. So because of its shape, the charges or the vectors will be cancelled. Then for H2O, since it's bent, so uh, so here the overall vector is different from the first one. So again, the shape of the molecule affects the overall polarity of the molecule.